Welcome, friends. He is so glad they are here. Whether they are drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, they have found the right place. Before the journey settles in, he wonders softly where in the world they are listening from. Perhaps they are wrapped in a blanket seated beside a dim window or resting somewhere beneath an open night sky. Wherever they are, he hopes they are warm, comfortable, and ready to wander into the quiet reaches of the universe, where a faint signal beneath Antarctic ice begins to trouble the calm architecture of physics. If they find peace or curiosity in these gentle explorations, he invites them to like the video, subscribe to the channel, or share it with someone who might need a moment of stillness too. And to those who have already joined along, gratitude rests quietly with them. Beneath kilometers of Antarctic ice at the geographic South Pole, detectors rest in silence, listening. The air is thin, the horizon unbroken, the cold so persistent it feels geological. Instruments such as those of the BICEP and Keck array experiments observe the sky in microwave frequencies, measuring faint polarization patterns in the cosmic microwave background, the afterglow of the Big Bang released, when the universe becomes transparent about 380,000 years after its beginning. That is a scientifically accepted fact. The cosmic microwave background, or CMB, forms during recombination, when electrons and protons combine into neutral hydrogen, allowing photons to travel freely. Only takes a few 100,000 years after the Big Bang for light to finally move without constant scattering. Only takes 13 billion more years for that light to be measured by chilled receivers at the bottom of the world. Only takes a planet with stable ice sheets to host such listening. The detectors search for B-mode polarization, a subtle twisting pattern in the microwave light that could reveal gravitational waves from cosmic inflation, a brief exponential expansion thought to occur fractions of a second after the Big Bang. Inflation is widely supported because it explains the universe's large-scale uniformity and flat geometry. Yet the precise mechanism remains uncertain. The poetic detail lies in the way this ancient light arrives, photons stretched by cosmic expansion until their wavelengths are millimeters long, like a planetary exhale that never quite finishes. They fall silently onto antennas, each photon older than any star now visible in the night sky. The mystery lingers in small irregularities, anomalies that appear slightly stronger or aligned in ways not perfectly predicted by the simplest inflationary models. Some regions show unexpected correlations across vast angular scales. The so-called axis of evil, a controversial alignment in CMB multipoles, remains debated. Is it statistical fluke, instrumental artifact, or faint hint of physics not yet described? No conclusion rests firmly. Only takes data at the limits of precision to unsettle equations written in confidence. Only takes improved calibration to either confirm or erase a cosmic suspicion. Only takes humility before background noise. The Antarctic ice itself becomes part of the experiment's quiet poetry. It is stable, dry, and nearly free of atmospheric water vapor, making it ideal for microwave observation. Beneath the surface, neutrinos from distant cosmic events pass through unnoticed, indifferent to ice or instrument. The Earth rotates, bringing different swaths of sky overhead, yet the detectors remain fixed, patient. There is a dry irony in how the universe's most ancient light is studied in one of Earth's youngest landscapes, shaped by ice sheets only millions of years old. Only took a recent ice age to prepare the stage for primordial photons. Only took tectonic drift to position Antarctica at the pole. Only took orbital geometry to stabilize long winters of darkness. The polarization patterns measured here are encoded with information about density fluctuations in the early universe. Quantum fluctuations stretch to cosmic scales. In standard cosmology, these fluctuations seed galaxies and clusters. Without them, matter would remain smooth. Stars would not ignite, and heavy elements would not form. It is a quiet fact that every atom of iron in human blood traces its existence to instabilities first whispered in the inflationary epoch. Yet the amplitude and distribution of these fluctuations show slight tensions with predictions derived from the simplest scalar field models. Some analyses suggest a mild suppression of power at large angular scales. Others note hints of non-Gaussianity beyond expectations. The evidence is subtle, statistically marginal, but persistent enough to encourage careful re-examination. The emotional tone remains flat. There is no crisis, only discrepancy. Physics is not collapsing. It is adjusting like ice settling under its own weight. Another mystery rests in foreground contamination. Galactic dust emits polarized microwave radiation, complicating the search for primordial signals. In 2014, an early claim of inflationary B modes is later understood to be largely dust emission from the Milky Way. Only took interstellar grains aligned with magnetic fields to imitate the universe's birth cry. Only took enthusiasm to briefly outrun caution. Only took further data to restore balance. The lesson remains measured: extraordinary signals demand extraordinary verification. Yet the pursuit continues because the reward is profound. Detecting primordial gravitational waves would anchor inflation not merely as theoretical convenience, but as physical event. It would link quantum mechanics and gravity and observational evidence, showing space-time itself trembling at energies unreachable by any terrestrial accelerator. The instruments continue their vigil. The sky remains patient. The CMB temperature averages 2.725 Kelvin uniform to 1 part in 100,000. That astonishing smoothness is itself a discovery that once forced physics to expand to invent inflation as explanatory framework. Now finer scrutiny of that same light suggests additional layers may await. Perhaps inflation is more complex than first imagined. Perhaps multiple fields interact. Perhaps new symmetries break in ways not yet modeled. Or perhaps statistical variance alone explains every anomaly. Uncertainty rests gently, not dramatically. Only takes more seasons of data. Only takes cross-correlation with satellite observations such as Planck. Only takes time, and physics has learned patience from the cosmos it studies. Under Antarctic stars, which appear to wheel slowly around a fixed point in the southern sky, detectors hum softly, ice creaks as temperatures shift by degrees. The universe expands imperceptibly, stretching ancient light even further. In that stretching, in that faint polarization pattern, traced against cold sky, lies the possibility that equations written a century ago may require subtle revision. Not replacement, not overthrow revision. Physics does not break, it refines. And so the whisper beneath the ice continues older than continents, quieter than snowfall, steady as the rotation of Earth itself. The echo of the first light continues to arrive without urgency, a uniform bath of microwave radiation filling all directions of the sky, discovered accidentally in 1965 by Arno Penzias and Robert Wilson as persistent noise in a horn antenna in New Jersey, a scientifically accepted moment that confirms the hot Big Bang model. The radiation measures today at 725 Kelvin, only a few degrees above absolute zero, its spectrum, almost a perfect blackbody curve, one of the most precise thermal distributions ever observed in nature. Only takes a universe once dense and hot to leave behind such equilibrium. Only takes expansion over 13.8 billion years to cool it into microwaves. Only takes sensitive receivers shielded from terrestrial interference to detect what seems like silence. Yet within this near-uniform glow lie fluctuations at the level of 1 part in 100,000 tiny variations in temperature mapped in exquisite detail by satellites such as COBE, WMAP, and Planck. These fluctuations are not noise but structure seeds, density differences that later grow under gravity into galaxies and clusters. The poetic detail rests in their delicacy variations, smaller than the difference between 2 grains of sand spread across an entire continent of sky. The universe writes its blueprint in faint gradients. Planck's full sky maps reveal acoustic peaks in the angular power spectrum signatures of pressure waves rippling through the primordial plasma before recombination. These baryon acoustic oscillations encode information about the universe's composition, roughly 5% ordinary matter, 27% dark matter, 68% dark energy under the standard lambda CDM model. This concordance model fits most data remarkably well, and yet, in the precision margins, small irregularities appear. Large angle anomalies persist, including hemispherical power asymmetry and the so-called cold spot, a region of slightly lower temperature spanning several degrees. Some analyses suggest it may be linked to a supervoid along that line of sight. Others argue it exceeds expectations from Gaussian fluctuations. The uncertainty remains unresolved. Only takes cosmic variance to blur certainty. Only takes limited observable volume to constrain statistics. Only takes humility before finite samples of an infinite-seeming sky. The cold spot itself is modest tens of microkelvin cooler than average, yet its existence invites speculation. It may simply be a rare statistical fluctuation, inevitable in a universe governed by probability distributions. It may be enhanced by integrated Sachs-Wolf effects, where photons lose or gain energy passing through evolving gravitational potentials, or it may hint at subtler physics. No conclusion asserts itself loudly. The sky remains quiet. There is a dry irony in how the universe's most ancient message appears almost perfectly smooth, as if complexity waits patiently for gravity to amplify it. Only took quantum fluctuations smaller than atoms to sculpt clusters spanning millions of light years. Only took gravity's steady pull acting without haste. Only took time, and the universe has been generous with that. Planck data also refined parameters, such as the Hubble constant, derived from early universe observations, yielding values around 67 kilometers per second, per megaparsec slightly lower than measurements from local distance ladders using Cepheid variables, and Type 1 a supernovae. That discrepancy, known as the Hubble tension, will deepen in later sections, but here it emerges quietly from the microwave background's pattern. The CMB does not shout disagreement. It implies it through fit residuals and likelihood contours. The scientific fact stands firm. Acoustic oscillations in the primordial plasma leave measurable peaks, corresponding to compressions and rarefactions governed by photon-baryon coupling. The lesser-known detail is that the sound horizon at recombination, about 150 megaparsecs today, becomes a cosmic ruler imprinted across large-scale structure. Galaxies remember a sound that has not existed for billions of years. The mystery lingers in why certain multipole alignments appear correlated beyond expectation. Some researchers question whether foreground subtraction or instrument systematics contribute. Others test exotic models involving topology or early anisotropic expansion. None achieves consensus. Only takes improved data releases to shift interpretation. Only takes alternate statistical priors to reshape significance. Only takes patience measured in decades. As Earth rotates beneath orbiting satellites, detectors cool to fractions of a degree above absolute zero to reduce thermal noise. The instruments themselves become part of the measurement, their calibration, a delicate art. Bolometers absorb single photons, converting energy into measurable heat differences. It is a soft paradox that to study the afterglow of a once blazing universe, instruments must be colder than interstellar space. Only took cryogenic engineering to approach primordial conditions. Only took vacuum chambers orbiting Earth to escape atmospheric interference. Only took collaborative effort across continents. The microwave background does not change perceptibly on human timescales. It is effectively static, a fossil radiation field. Yet its photons continue to redshift as space expands, their wavelengths stretching slowly. In another 100 billion years, they will be so diluted and redshifted that detection may become impossible from within any gravitationally bound remnant. Future astronomers, if they exist, may see no evidence of the Big Bang at all. There is a quiet irony in that. Only took accelerated expansion to hide the origin story. Only took cosmic horizons to limit memory. Only took dark energy to dim the archive. For now, the echo remains accessible. Its near-perfect blackbody curve constrains exotic energy injection scenarios. Its polarization maps test ionization history. Its lensing patterns trace dark matter distribution between us and the last scattering surface. Every pixel contains layered information. And yet, despite the model's success, the anomalies do not fully dissolve. They are statistically subtle, never rising to incontrovertible proof of new physics, but persistent enough to keep theorists attentive. The universe offers consistency, wrapped in slight irregularity, like stone worn smooth but never flawless. Physics adjusts by refining parameters, exploring inflationary potentials beyond the simplest slow-roll scenario, considering early dark energy components or testing variations in neutrino properties. The microwave sky becomes a canvas for these possibilities. Beneath Antarctic ice and within orbiting observatories, detectors continue their steady listening. The first light emitted when the universe is young and opaque. no longer still carries imprints of epochs far earlier, when inflation may have stretched quantum fluctuations beyond atomic scales. The echo is ancient, yet current, arriving now, entering antennas, now recorded in data sets processed now. It does not announce revolution. It suggests reconsideration. And in that suggestion, physics remains open, not broken, not undone, but attentive to faint departures from expectation written across the oldest light in existence. Gravity's uneasy equation rests quietly at the center of modern cosmology, written in 1915, when Albert Einstein presents general relativity, describing gravity not as force, but as curvature of space-time produced by mass and energy, a scientifically accepted framework that has passed every classical test, from Mercury's perihelion precession to gravitational lensing and time dilation near massive bodies. The field equations are compact, almost austere, relating geometry to energy momentum through tensor relationships that curve light and bend trajectories. Only takes mass to tell space-time how to curve. Only takes curvature to tell matter how to move. Only takes patience to verify predictions across a century. Yet when these equations are applied to the universe as a whole, combined with assumptions of large-scale homogeneity and isotropy, they yield the Friedmann equations, which describe expansion. Observations in the late 20th century reveal that this expansion is accelerating, inferred from distant type 1, a supernovae appearing dimmer than expected, leading to the reintroduction of Einstein's cosmological constant lambda, interpreted today as dark energy. That discovery in 1998 becomes a cornerstone of the lambda CDM model. Only took exploding white dwarfs billions of light-years away to reveal acceleration. Only took careful calibration of standard candles. Only took a willingness to accept that empty space might possess energy density. Dark energy, as currently modeled, behaves like a constant energy density filling space, uniformly exerting negative pressure that drives accelerated expansion. Its value is extraordinarily small in everyday units, yet dominates the cosmic energy budget. The poetic detail rests in its subtlety, a force so weak it cannot be detected in laboratories, yet so persistent it shapes the fate of the universe. The mystery, however, lies in its magnitude. Quantum field theory predicts vacuum energy densities many orders of magnitude larger than observed, a discrepancy sometimes called the cosmological constant problem. The predicted value exceeds observations by as much as 10 to the power of 120 in naive calculations. Only takes a mismatch of unimaginable scale to unsettle confidence. Only takes quantum fluctuations summed across modes to produce infinities. Only takes renormalization to obscure deeper origin. General relativity and quantum field theory coexist uneasily here. On astrophysical scales, relativity works beautifully. On subatomic scales, quantum mechanics governs with equal success. But when vacuum energy from quantum fields is inserted into Einstein's equations, the resulting curvature would be catastrophic, not gentle acceleration. Something is incomplete in the synthesis. The tension does not overthrow relativity. Rather, it suggests that understanding of vacuum energy or gravity's coupling to it is unfinished. Observationally, acceleration is supported by multiple probes beyond supernova baryon acoustic oscillations trace expansion history. The cosmic microwave background constrains geometry. Weak gravitational lensing maps matter distribution over cosmic time. Together, they outline a universe that transitions from decelerating expansion dominated by matter to accelerating expansion dominated by dark energy roughly 5 billion years ago. Only took half the universe's current age for acceleration to begin. Only took gravity's gradual weakening as density diluted. Only took a component that does not dilute with expansion. Yet alternative explanations remain explored. Modified gravity theories adjust Einstein's equations at large scales, proposing that curvature behaves differently across cosmic distances. Some introduce scalar fields that vary over time known as quintessence, allowing dark energy to evolve rather than remain constant. Observations so far remain consistent with a cosmological constant within uncertainties, but the possibility of slow variation has not been entirely excluded. The quiet scientific uncertainty persists in the equation of state parameter W defined as pressure divided by energy density. If W equals -1 exactly, dark energy is consistent with a cosmological constant. Measurements constrain W close to -1, yet small deviations remain within error margins. Only takes slight deviation to suggest new physics. Only takes tighter constraints from future surveys to narrow the range. Only takes time and data. There is a gentle irony in how gravity, once considered the most familiar of forces, becomes the least understood at cosmic scales. It governs falling apples and planetary orbits, yet when stretched across billions of light-years, it requires invisible components, dark matter and dark energy, to reconcile observation with equation. Only took galactic rotation curves to reveal unseen mass. Only took cluster lensing to confirm it. Only took acceleration to introduce energy that does not clump. Dark matter itself interacts gravitationally, but not electromagnetically, shaping structure formation. Without it, galaxies would not form as observed. Yet its particle nature remains unidentified despite decades of searches. Thus, gravity's equation binds together two unknowns, dark matter and dark energy. General relativity remains structurally intact, but the contents of the universe it describes are partially invisible. Observatories now refine expansion measurements through gravitational wave events known as standard sirens. When binary neutron stars merge, gravitational waves carry distance information independent of traditional distance ladders. Coupled with electromagnetic counterparts, they provide alternative estimates of the Hubble constant. Early measurements hint at values that may align more closely with local expansion rates than with CMB-derived values, though uncertainties remain large. The possibility that gravity's behavior or dark energy's properties differ slightly from standard assumptions lingers as explanation for the Hubble tension. The equations are not discarded. They are examined at their edges. Only takes discrepancies of a few kilometers per second per megaparsec to prompt reconsideration. Only takes precision cosmology to expose tension. Only takes cumulative evidence to justify revision. On Earth, laboratories test general relativity in strong and weak regimes, measuring gravitational redshift, frame dragging, and gravitational waves from black hole mergers. So far, Einstein's predictions endure. The unease arises not from failure, but from incompleteness, from parameters inserted to fit data whose deeper origins remain unknown. The universe appears governed by geometry, Yet geometry seems influenced by components not fully understood. It is as if spacetime itself carries a quiet remainder in its accounting. In the calm of cosmic expansion, gravity continues its dual role, attracting matter, locally driving acceleration globally through dark energy's influence. The uneasy equation remains elegant, compact, and profoundly successful, yet surrounded by mysteries that encourage gentle revision rather than collapse. Physics stands not on the brink of overthrow, but in the process of refinement guided by data that whisper rather than shout. Gravity curves, space expands, the equations hold, and still something subtle asks to be understood more deeply. The Hubble tension does not erupt. It accumulates. It begins as a difference so small it almost seems clerical, a few kilometers per second, per megaparsec. Yet in cosmology, such a difference is structural. The Hubble constant h0 measures the present rate at which the universe expands. In the early universe, its value is inferred indirectly from the cosmic microwave background, assuming the lambda CDM model and projecting forward. That inference yields a value near 67 kilometers per second, per megaparsec. In the late universe, astronomers measure h0 more directly by building a cosmic distance ladder calibrating Cepheid variable stars, then Type 1a supernovae, and extending outward to distant galaxies. Those measurements consistently cluster near 73 kilometers per second per megaparsec. Only takes a 5 to 6 kilometer discrepancy to unsettle a concordance model. Only takes independent methods agreeing internally, yet disagreeing with each other. Only takes shrinking error bars to transform curiosity into tension. Cepheid variables obey a well-established period luminosity relation first discovered by Henrietta Leavitt, a scientifically accepted tool that allows intrinsic brightness to be inferred from pulsation period. Type 1. A supernovae arising from thermonuclear explosions of white dwarfs near the Chandrasekhar limit serve as standardizable candles because their peak luminosities correlate with light curve shape. These are not speculative tools. They are refined across decades. The poetic detail lies in how stars that pulse gently in nearby galaxies become rungs in a ladder stretching across billions of light years. The universe expands and small rhythmic flickers measure it. Yet even after recalibrations using parallax from the Gaia spacecraft, even after careful accounting for dust extinction and metallicity effects, the higher local value persists. The tension now exceeds 5 standard deviations, in some analyses statistically significant by conventional standards. The mystery rests in its source. Is there unrecognized systematic error in the distance ladder? Or is the early universe inference incomplete, missing a physical ingredient between recombination and today only takes overlooked astrophysical bias to skew a ladder? Only takes unmodeled early energy component to shift acoustic peaks. Only takes patience to test both possibilities. Alternative approaches attempt independence from both methods. Time delay cosmography uses gravitational lensing when a massive foreground galaxy bends light from a background quasar. Multiple images appear, each following a slightly different path. Variations in quasar brightness arrive at different times depending on path length and gravitational potential. Measuring these delays allows distance estimation and hence h0 determination. Several such measurements lean toward the higher local value, though uncertainties remain. Gravitational wave standard sirens provide yet another route, as binary neutron-star mergers yield luminosity distances directly from waveform amplitude. When electromagnetic counterparts identify host galaxies, redshift can be measured, providing H0 estimates without a traditional ladder. Early results are broad but promising. Only took ripples in space-time itself to join the measurement effort. Only took interferometers capable of detecting distortions smaller than a proton. Only took a merging pair of neutron stars 130 million light-years away to offer an independent check. The tension's persistence encourages theoretical exploration. One possibility introduces early dark energy, a transient component present before recombination, that briefly alters expansion history, shifting sound horizon scale and reconciling CMB inference with higher present expansion rates. Such models must fit not only H0, but also large-scale structure data and primordial nucleosynthesis constraints. Another avenue considers additional relativistic particles, sometimes described as dark radiation, that modify early universe dynamics. Others explore slight curvature deviations or interactions between dark matter and dark energy. None yet achieves consensus without introducing its own complications. The irony is quiet. The standard model of cosmology fits an enormous range of data with remarkable simplicity, yet a few percent discrepancy resists dismissal. Only took a universe billions of years old to reveal a small accounting gap. Only took improvements in telescope sensitivity to expose it. Only took precision to challenge comfort. The tension does not imply that general relativity fails outright. Rather, it suggests that either astrophysical calibration or cosmological composition may require adjustment. Future missions, such as the James Webb Space Telescope, refine Cepheid and supernova measurements at greater distances, reducing uncertainties tied to crowding and dust. Large-scale surveys, such as the Dark Energy Survey and upcoming Euclid mission map, millions of galaxies constraining expansion and structure growth simultaneously. The universe becomes a laboratory measured in photons rather than glassware. The lesser-known detail rests in how metallicity, the abundance of elements heavier than helium, can subtly affect Cepheid brightness, requiring corrections that depend on galactic environment. Even small shifts in metallicity calibration can nudge H0 values. The mystery remains whether cumulative small effects explain the full discrepancy. Only takes layered corrections to alter outcome. Only takes cross-checking between independent teams to test robustness. Only takes time measured in survey cycles. As expansion proceeds, the light from distant galaxies redshifts, stretching like ink, drawn thin across the page of space-time. The Hubble constant is not truly constant across cosmic time. It evolves as density components change. The measured H0 is a present-day snapshot. Reconciling early and late snapshots becomes a question of intervening physics. The tension is not loud, it is statistical. It does not fracture cosmology. It invites scrutiny, and scrutiny is a discipline of calm repetition, not drama. Observatories refine parallax to micro-arc-second precision. Supernova light curves are modeled with increasingly sophisticated algorithms. Gravitational lensing mass distributions are reconstructed through detailed modeling of stellar kinematics and dark matter halos. The process is iterative and quiet. Only took decades to build the latter. Only takes more decades to reinforce or rebuild it. In this measured disagreement, physics does not collapse. It stretches. The expansion of the universe, once controversial, is now foundational. Acceleration, once astonishing, is now incorporated. A discrepancy of several percent now occupies center stage. Whether it signals new particles evolving dark energy, subtle systematic error, or some deeper modification remains open. The universe continues expanding while cosmologists compare likelihood functions. Beneath the calm of redshift surveys and pulsating stars, the question persists. Does the early universe tell a slightly different story than the late universe? Or are observers misreading one of them? The answer is not yet settled. The tension deepens not as crisis, but as invitation. If the Hubble tension unsettles expansion, dark matter unsettles substance. It does not glow, absorb, scatter, or radiate in any wavelength accessible to telescopes. It reveals itself only through gravity, through motion and lensing and structure. The evidence is cumulative and geometric rather than luminous. In spiral galaxies, stars orbit with speeds that remain unexpectedly flat, far from the center rather than declining, as Newtonian expectations based solely on visible matter would predict. The classic rotation curve measurements by Vera Rubin and her collaborators showed that outer stars circle as quickly as inner ones, implying an unseen mass halo extending well beyond the luminous disk. Only takes stars moving too fast to imply something invisible holds them in orbit. Only takes careful spectroscopic measurements of Doppler shifts across galactic disks. Only takes consistency across many galaxies to move anomaly toward acceptance. The concept of dark matter predates Rubin. Fritz Zwicky in the 1930s studied the Coma cluster and concluded that galaxies moved too rapidly within it to be gravitationally bound by visible mass alone, coining the term dunkle materia. His calculation used the virial theorem relating kinetic and potential energy in gravitational systems. For decades, the idea remained marginal, yet successive observations reinforced it. Gravitational lensing. The bending of light predicted by general relativity provided independent confirmation. When massive clusters distort and magnify background galaxies, the lensing pattern maps total mass distribution, luminous and non-luminous alike. The separation between hot X-ray gas and gravitational mass in merging systems, such as the Bullet cluster, offers striking visual evidence. Baryonic matter and gravitational centers do not coincide, suggesting a collisionless component. Only takes space-time curvature to trace what cannot be seen. Only takes background galaxies stretched into arcs to outline mass contours. Only takes alignment between independent methods to build confidence. Cosmological simulations incorporating cold, dark matter reproduce large-scale filamentary structures observed in galaxy surveys. Without dark matter, the growth of structure from tiny primordial fluctuations would be too slow to produce galaxies by the present epoch. Dark matter acts as scaffolding gravitational wells, forming early drawing baryonic gas inward where stars ignite. The lesser-known detail lies in the role of dark matter in cosmic microwave background anisotropies. Its presence affects acoustic peak heights in the power spectrum altering the ratio between odd and even peaks by influencing gravitational potential wells during recombination. The lambda CDM model. Lambda cold dark matter remains the standard cosmological framework because it accounts simultaneously for expansion history structure formation and CMB measurements. Yet dark matter's particle nature remains unknown. Candidates range from weakly interacting massive particles, WIMPs, to axions, sterile neutrinos, and other hypothetical species. Direct detection experiments attempt to measure rare interactions between dark matter particles and atomic nuclei deep underground, shielded from cosmic rays. So far, none has produced unambiguous detection. Only takes years of null results to narrow parameter space. Only takes improved sensitivity to close theoretical windows. Only takes silence in detectors to redirect effort. Indirect searches look for annihilation or decay products, excess gamma rays or positrons from regions dense with dark matter. Observations have produced intriguing hints, but no definitive signature. Collider experiments, such as those at the Large Hadron Collider, search for missing energy events that might signal dark matter production. The interplay between astrophysical observation and particle physics experiment defines the modern approach. Meanwhile, alternative theories challenge the premise of unseen matter by modifying gravity at low accelerations. Modified Newtonian dynamics. Maundy proposes adjustments to Newton's law below a characteristic acceleration scale, successfully reproducing many galactic rotation curves without invoking dark matter halos. However, Mund struggles to explain cluster dynamics and cosmological observations simultaneously. Relativistic extensions attempt to address these issues, but consensus remains elusive. Only takes a galaxy rotation curve to motivate modification. Only takes cluster scale discrepancies to strain it. Only takes cosmic background data to favor particle dark matter. The philosophical question persists: is dark matter a particle awaiting detection, or a signal that gravity behaves differently at galactic scales? Most evidence favors a particulate explanation, yet absence of direct detection sustains caution. Dark matter composes roughly 27% of the universe's energy density, dwarfing the roughly 5% constituted by ordinary baryonic matter. The remainder, approximately 68%, belongs to dark energy, the driver of accelerated expansion. The cosmic inventory is dominated by entities neither seen nor fully understood. The lesser-known nuance lies in small-scale structure. Problems simulations predict more satellite galaxies around systems like the Milky Way than observed and cusp-like central density profiles rather than the flatter cores sometimes inferred. Solutions may involve baryonic feedback processes, such as supernova-driven gas outflows, reshaping dark matter distributions, or they may hint at slightly warmer dark matter particles that suppress small-scale clustering. Only takes a dwarf galaxy census to raise questions. Only takes refined simulations, including star formation physics, to reconcile discrepancies. Only takes resolution improvements to shift apparent tensions. On galactic scales, dark matter halos are thought to follow Navarro-Frank-White profiles derived from numerical simulations. On cluster scales, lensing maps and X-ray observations align with cold, dark matter predictions. On cosmological scales, large surveys trace baryon acoustic oscillations consistent with lambda CDM parameters. The web of evidence interlocks. Yet at the particle level, the silence continues. Axion searches employ resonant cavities immersed in strong magnetic fields, attempting to convert hypothetical axions into detectable photons. Underground cryogenic detectors wait for minute energy deposits from nuclear recoils. Neutrino observatories search for annihilation signatures from the sun's core, where dark matter might accumulate. Each approach narrows theoretical space. Only takes incremental sensitivity gains to exclude entire classes of models. Only takes cross-disciplinary persistence to maintain direction. Dark matter shapes galaxies quietly. It stabilizes disks, influences bar formation, and governs merger dynamics. It dictates how clusters assemble and how filaments stretch across cosmic voids. Yet it does not shine. The paradox of cosmology is that the visible universe is minority content. Stars, nebulae, planets, all luminous structures ride within invisible halos. The night sky appears full, but its substance is sparse compared to what binds it. The mystery deepens not because evidence is lacking, but because identity is. The gravitational footprint is clear. The microscopic fingerprint is absent. Whether the next breakthrough comes from deep underground detectors, from precision lensing surveys, or from unexpected anomalies in cosmic surveys remains unknown. Dark matter's role in cosmic evolution is secure. Its nature is not. The scaffolding stands. The material remains unnamed. Only takes unseen mass to anchor galaxies. Only takes gravitational arcs to reveal it. Only takes continued observation to close the gap between inference and understanding. The universe continues its expansion, its acceleration, its quiet rotation of stars within halos. Dark matter remains central yet silent, a structural necessity without direct signature. In the inventory of cosmic mysteries, it occupies not a marginal footnote, but a primary column. And like the Hubble tension before it, its resolution likely lies not in dramatic overturn, but in measured accumulation, deeper surveys, subtler detectors, refined models. The invisible persists not as absence, but as gravitational presence awaiting identification. If dark matter governs structure and the Hubble tension unsettles expansion, dark energy governs fate. It is not merely an additive term in cosmological equations. It is the dominant component of the universe's energy density, shaping its long-term trajectory. The discovery that cosmic expansion is accelerating emerged in the late 1990s from observations of distant Type 1, a supernovae conducted independently by the Supernova Cosmology Project and the High Z Supernova Search Team. The supernovae appeared dimmer than expected in a decelerating universe, implying that expansion had sped up over the last several billion years. Only takes standardizable candles at cosmological distances to reveal acceleration. Only takes comparing redshift to luminosity distance. Only takes careful calibration across cosmic time to overturn expectation. The simplest explanation is the cosmological constant lambda, originally introduced by Albert Einstein in 1917 as a modification to general relativity to permit a static universe, later abandoned when expansion was observed and now reinstated with new meaning. In modern interpretation, lambda corresponds to vacuum energy, an intrinsic energy density of empty space that remains constant as the universe expands. In the Friedmann equations governing cosmic dynamics, this constant energy density exerts negative pressure driving accelerated expansion. The mathematics is concise, the implications are vast, only takes a term proportional to the metric tensor, only takes pressure equal to minus energy density, only takes integration over cosmic time to see acceleration emerge. Yet the cosmological constant presents a profound theoretical puzzle. Quantum field theory predicts that vacuum fluctuations contribute energy to empty space. When calculated naively, the expected vacuum energy density exceeds observed dark energy density by an enormous factor often quoted as 10 to the power of 120, the largest known discrepancy between theory and observation in physics. Even with more conservative cutoffs, the mismatch remains staggering. The lesser-known detail lies in renormalization subtleties. Vacuum energy can be shifted by counterterms, but gravity responds to absolute energy density, not merely differences. Reconciling quantum vacuum contributions with observed lambda remains unresolved. Only takes summing zero-point energies of quantum fields. Only takes Planck scale assumptions to inflate predictions. Only takes observational measurement to constrain reality. Alternative explanations propose that dark energy is not constant, but dynamic, described by a scalar field slowly evolving over time, often termed quintessence. In such models, the equation of state parameter W defined as pressure divided by energy density may deviate slightly from -1, the value corresponding to a pure cosmological constant. Observational programs measure W through supernova surveys, baryon acoustic oscillations, and weak gravitational lensing. Thus far, data remain consistent with W approximately -1 within uncertainties. Only takes tightening error bars to test deviation. Only takes mapping large-scale structure growth to constrain models. Only takes patience across survey generations. The geometry of the universe intertwines with dark energy. Measurements of cosmic microwave background anisotropies indicate spatial flatness to high precision, implying that total energy density equals critical density. Within that budget, dark energy fills most of the ledger. Its uniform distribution contrasts with the clumped nature of matter. While dark matter gathers into halos and filaments, dark energy appears smooth across space. This smoothness drives acceleration uniformly rather than locally. The expansion does not feel like a force pushing galaxies through space. Rather, space itself stretches increasing proper distances between gravitationally unbound systems. Only takes metric expansion to separate clusters. Only takes cosmic time to amplify effect. Only takes local gravity to resist within bound systems. On scales of galaxies and clusters, gravity dominates. Dark energy's influence is negligible. On scales between clusters, it governs separation. The long-term future of the universe depends on dark energy's nature. If it remains a cosmological constant expansion, will continue accelerating galaxies beyond the local group, eventually receding beyond our observable horizon. The cosmic microwave background will redshift further cooling toward invisibility. Star formation will decline as gas is consumed or expelled. The universe trends toward a cold, dilute state often described as heat death. If dark energy evolves differently, other scenarios arise. In phantom energy models where W is less than -1, expansion accelerates so dramatically that bound structures could eventually be torn apart in a hypothetical Big Rip. In models where dark energy decays or reverses, sign acceleration could slow or transition to contraction. Current observations favor steady acceleration, yet the precision required to distinguish subtle time variation remains demanding. Only takes a fractional shift in W to alter destiny. Only takes billions of years for differences to magnify. Only takes consistent measurement to narrow possibilities. The interplay between dark energy and structure formation is delicate. As acceleration increases, growth of large-scale structure slows because gravitational collapse competes with expanding space. Surveys mapping weak lensing distortions across millions of galaxies quantify how matter clusters over time, indirectly probing dark energy's influence. The lesser-known nuance involves degeneracy between dark energy parameters and neutrino masses. Massive neutrinos suppress small-scale structure growth, potentially mimicking certain dark energy signatures. Thus, cosmology links particle physics parameters with cosmic acceleration. Only takes sub-electron volt neutrino masses to affect clustering. Only takes combined datasets to disentangle effects. Only takes statistical rigor to avoid misattribution. The cosmological constant also intersects with philosophical considerations. Why does dark energy density become dynamically significant only in the recent cosmic epoch? In earlier eras, radiation and matter densities dominated. Only after billions of years did the constant vacuum energy surpass them. This coincidence problem raises questions about anthropic reasoning and multiverse hypotheses. Some argue that a range of vacuum energies might exist across a broader landscape, with observers naturally arising in regions where structure formation is possible. Such ideas remain speculative yet persistent. Only takes parameter sensitivity to restrict galaxy formation. Only takes slight increases in lambda to prevent structure entirely. Only takes life's existence to provoke reflection. Precision cosmology continues refining constraints. Large spectroscopic surveys measure baryon acoustic oscillation scales as standard rulers across redshift tracking expansion history. Supernova samples grow in size and redshift coverage. Gravitational wave standard sirens may eventually contribute independent distance measures across cosmic time. Each method converges on a consistent picture of acceleration. Yet theoretical understanding lags observational certainty. Dark energy is inferred with high confidence. Its origin remains obscure. The tension between measurement and mechanism parallels that of dark matter. Gravitational signature without particle identification, acceleration without field detection. Only takes equations that fit data. Only takes deeper theory to explain constants. Only takes humility before unknown parameters. As expansion accelerates, distant galaxies cross event horizons defined not by black holes, but by cosmic geometry. Light emitted beyond a certain distance today will never reach us in the future, because space between us expands too rapidly. The observable universe becomes gradually emptier, not by loss, but by recession. The future sky for distant observers will contain fewer galaxies. Cosmology becomes archival science, reconstructing a richer past from limited signals. Dark energy ensures that cosmic history is more accessible than cosmic future. In the quiet mathematics of Friedman, Lemaitre-Robertson-Walker metrics acceleration appears as scale factor curvature over time. In observational data, it appears as dim supernovae and stretched standard rulers. In philosophical reflection, it appears as a question about vacuum energy and the nature of empty space. The universe expands not only in size but in mystery. Dark energy occupies the largest share of the cosmic budget, yet remains the least understood. Only takes one constant term to dominate fate. Only takes refined observation to confirm its persistence. Only takes continued theoretical effort to bridge the gulf between quantum fields and cosmological expansion. The expansion continues, the scale factor grows, and the unknown component persists, smooth, pervasive, mathematically simple, physically enigmatic, shaping destiny on scales too vast for direct intuition, yet measurable through careful accumulation of distant light. Black holes concentrate gravity to its most uncompromising expression, compressing mass into regions where escape velocity exceeds the speed of light and classical intuition collapses. They are not merely dense objects. They are boundaries in space-time defined by event horizons beyond which information cannot return to distant observers. The mathematical foundation arises from solutions to Einstein's field equations in general relativity. In 1916, Karl Schwarzschild derived the first exact solution describing the space-time geometry around a non-rotating spherical mass. The Schwarzschild radius marks the boundary at which the metric coefficient governing radial distance diverges in coordinate form, though the true physical singularity lies deeper where curvature scalars diverge. Only takes sufficient mass compressed within its Schwarzschild radius to form an event horizon. Only takes gravitational collapse of a massive star's core after nuclear fuel exhaustion. Only takes surpassing neutron degeneracy pressure to trigger irreversible implosion. Stellar mass black holes form when stars several times more massive than the Sun exhaust fusion pathways and core pressure fails against gravity. Supernova explosions expel outer layers while the core collapses inward. If the remnant mass exceeds the Tolman-Oppenheimer-Volkoff limit, no known force halts collapse. At the center, classical theory predicts a singularity, a point of infinite density and curvature. Whether true singularities exist in physical reality or signal breakdown of classical theory remains unresolved. The lesser-known detail lies in coordinate choices. What appears as singular behavior at the event horizon in Schwarzschild coordinates vanishes under Kruskal-Shekaris coordinates, revealing that the horizon is not a physical surface, but a causal boundary. Only takes a coordinate transformation to clarify geometry. Only takes proper time along infalling world lines to show finite passage across the horizon. Only takes global space-time diagrams to visualize causal structure. Rotating black holes described by the Kerr solution introduce additional complexity. Angular momentum drags space-time itself, producing frame-dragging effects measurable even near Earth, but extreme near rotating horizons. The Kerr metric predicts an ergosphere outside the event horizon, where no object can remain stationary relative to distant observers. Within this region, energy extraction becomes theoretically possible via the Penrose process, whereby particles split and one fragment escapes with greater energy than the original infalling particle. Only takes rotation to twist spacetime. Only takes conservation laws to permit extraction. Only takes relativistic jets to hint at astrophysical realization. Supermassive black holes reside at centers of most galaxies, including the Milky Way. The object known as Sagittarius A star contains roughly 4 million solar masses within a region smaller than our solar system. Stellar orbits measured over decades trace elliptical paths, consistent with a compact mass concentration. The Event Horizon Telescope collaboration produced the first horizon-scale images of supermassive black holes, first in Messier 87 and later of Sagittarius A star. These images reveal bright emission rings shaped by photon orbits and gravitational lensing around the shadow of the event horizon. Only takes radio interferometry spanning Earth's diameter to resolve such scales. Only takes synchronizing telescopes across continents with atomic clocks. Only takes reconstructing sparse Fourier data into coherent images. Accretion disks around black holes convert gravitational potential energy into radiation with efficiencies surpassing nuclear fusion. As gas spirals inward, viscous and magnetic stresses heat plasma to extreme temperatures, producing X-rays and relativistic jets that can extend thousands of light years. Active galactic nuclei outshine entire galaxies powered by accretion onto supermassive black holes. Yet despite dramatic luminosity, the horizon itself emits nothing classically. It is the surrounding matter that shines. The paradox emerges when quantum mechanics enters. In 1974, Stephen Hawking showed that black holes are not entirely black. Quantum field theory in curved spacetime predicts that particle-antiparticle pairs near the horizon can result in net radiation escaping to infinity, a process now termed Hawking radiation. The temperature of this radiation is inversely proportional to black hole mass. Stellar and supermassive black holes radiate at temperatures far below cosmic microwave background levels, rendering evaporation negligible over cosmic timescales. Only takes vacuum fluctuations near a horizon. Only takes quantum field modes straddling causal boundaries. Only takes semi-classical approximation to derive thermal spectrum. Hawking radiation introduces the black hole information paradox. If radiation is purely thermal, it carries no information about the matter that formed the black hole. Complete evaporation would seemingly erase information, violating quantum unitarity. Resolving this paradox remains a central challenge in theoretical physics. Proposed solutions involve subtle correlations in radiation holographic principles and the idea that information is encoded on the horizon surface area rather than volume and insight formalized in the Bekenstein-Hawking entropy formula, where entropy is proportional to horizon area divided by Planck area. Only takes linking thermodynamics and gravity. Only takes associating entropy with geometry. Only takes Planck scale considerations to hint at quantum gravity. Black hole mergers detected through gravitational waves by observatories such as LIGO and Virgo provide direct evidence of dynamic spacetime curvature. Waveforms match predictions from numerical relativity simulations, solving Einstein's equations under extreme conditions. The ring-down phase following merger reflects quasi-normal modes determined by mass and spin of the remnant black hole. Only takes spacetime ripples traveling at light speed. Only takes kilometer-scale interferometers detecting strains smaller than 10 to the power of -21. Only takes matching waveform templates to confirm theory. Black holes also test cosmic censorship conjectures, which propose that singularities formed through gravitational collapse are always hidden behind horizons, preventing naked singularities from affecting distant observers. While widely believed, the conjecture lacks formal proof. Similarly, the no-hair theorem asserts that stationary black holes are fully described by mass charge and angular momentum, with no additional independent parameters. Observational tests continue examining whether astrophysical black holes conform precisely to Kerr predictions or display subtle deviations. Only takes precision measurement of orbits near horizons. Only takes gravitational wave spectroscopy to constrain multipole moments. Only takes comparing theory to observation to probe limits. The interplay between black holes and galaxy evolution is profound. Feedback from accretion-driven jets can regulate star formation by heating or expelling interstellar gas. Correlations between black hole mass and stellar velocity dispersion. The M-sigma relation suggests coevolution between central black holes and their host galaxies. Whether black holes seed galaxy formation or grow alongside it remains under investigation. Only takes empirical correlation to imply connection. Only takes feedback models to simulate regulation. Only takes observational campaigns across wavelengths to map influence. At the frontier of theory, black holes intersect with attempts at quantum gravity. In string theory, certain supersymmetric black holes allow microstate counting consistent with Bekenstein-Hawking entropy, providing partial insight into microscopic degrees of freedom. In loop quantum gravity, quantized spacetime areas yield discrete horizon spectra. The holographic principle inspired by black hole thermodynamics proposes that a higher dimensional gravitational theory can be equivalent to a lower dimensional non-gravitational field theory, as exemplified by the ADS/CFT correspondence. Only takes boundary bulk duality to reshape perspective. Only takes mapping gravity to gauge theory to bridge frameworks. Only takes persistent paradox to motivate innovation. Black holes, once speculative mathematical curiosities, now occupy observational catalogs and theoretical centrality. They bend, light-generate jets, emit gravitational waves, and radiate quantum mechanically. They define limits of density and curvature, challenge integration of general relativity and quantum mechanics, and shape galactic ecosystems. Yet their interiors remain inaccessible, hidden beyond horizons that preserve causal separation. The singularity predicted by classical equations may be replaced by quantum structure, but until a full theory emerges, speculation continues within mathematical constraints. Only takes collapsing stars to form them. Only takes space-time curvature to describe them. Only takes quantum considerations to complicate them. In their silence and intensity, black holes represent both confirmation and frontier confirmation that general relativity withstands extreme tests. Frontier, because reconciliation with quantum theory remains incomplete. They are endpoints of stellar evolution and gateways to deeper physics, compact, yet conceptually expansive. As observations refine and detectors grow more sensitive, black holes transition from theoretical boundary conditions to empirical laboratories, The event horizon marks not an end of inquiry, but a beginning where gravity, thermodynamics, and quantum theory converge in a region both physically small and intellectually vast. The early universe does not begin with galaxies or stars, but with plasma and symmetry. To trace it backward is to compress temperature density and curvature into regimes where known physics approaches its limits. Cosmology reconstructs this history not through direct observation of the first instance, but through relics, background radiation, light element, abundances, large-scale structure, each a fossil of earlier conditions. The standard narrative begins with a hot, dense state described by the Friedmann equations under general relativity, yet extrapolation toward time zero yields a singularity where density and temperature diverge. Whether that singularity represents physical reality or signals the breakdown of classical theory remains open. Only takes reversing expansion mathematically to approach divergence. Only takes assuming classical spacetime persists arbitrarily backward. Only takes acknowledging that quantum gravity likely intervenes. Before approximately 10 to the power of minus 43 seconds, the Planck time quantum gravitational effects are expected to dominate. No complete theory yet describes this epoch. After that threshold, the universe is thought to have undergone cosmic inflation, a period of exponential expansion driven by a high-energy scalar field. Inflation was proposed to address several puzzles: the horizon problem, the flatness problem, and the absence of magnetic monopoles predicted by grand unified theories. Without inflation, regions of the cosmic microwave background, separated by more than a few degrees on the sky, would not have been causally connected prior to recombination, yet they exhibit nearly identical temperatures. Only takes exponential expansion to stretch a tiny causally connected region beyond observable scales. Only takes rapid growth of the scale factor to dilute curvature toward flatness. Only takes quantum fluctuations magnified to cosmic size to seed structure. The concept of inflation was first articulated by Alan Guth and later refined into slow-roll models by others. During inflation, vacuum energy associated with the inflaton field dominated, driving accelerated expansion, similar in mathematical form to dark energy, but at vastly higher energy scales. Quantum fluctuations in the inflaton and metric became classical density perturbations as wavelengths stretched beyond the horizon. These perturbations later re-entered during radiation and matter domination, forming the seeds of galaxies and clusters. The nearly scale-invariant spectrum of primordial fluctuations predicted by inflation matches measurements of the cosmic microwave background with remarkable precision. Only takes mapping temperature anisotropies across the sky. Only takes decomposing fluctuations into spherical harmonics. Only takes comparing power spectra with theoretical curves. The cosmic microwave background, first detected in 1965 by Arno Penzias and Robert Wilson, provides a snapshot of the universe approximately 380,000 years after the Big Bang, when electrons and protons combined to form neutral hydrogen and photons decoupled from matter. Its temperature is uniform to 1 part in 100,000, yet slight anisotropies encode information about primordial conditions. Satellite missions such as COBE WMAP and Planck have mapped these anisotropies with increasing resolution constraining cosmological parameters to percent-level precision. The lesser-known detail lies in polarization patterns. E-mode polarization arises from Thomson scattering in a quadrupole radiation field at recombination, while B-mode polarization could signal primordial gravitational waves from inflation. Detecting primordial B-modes remains a major goal, as it would provide evidence of inflation's energy scale. Only takes measuring microkelvin fluctuations. Only takes filtering foreground dust contamination. Only takes isolating subtle curl patterns in polarization maps. As the universe expanded and cooled further, Big Bang nucleosynthesis occurred within the first few minutes, producing light nuclei, primarily hydrogen-helium, 4 deuterium-helium-3, and trace lithium-7. Predicted abundances depend sensitively on baryon-to-photon ratio and nuclear reaction rates. Observations of primordial deuterium in distant gas clouds align closely with theoretical predictions reinforcing the hot Big Bang framework. Yet the lithium problem persists. Predicted lithium-7 abundance exceeds what is observed in old metal-poor stars. Whether this discrepancy arises from stellar processes depleting lithium or from new physics affecting nucleosynthesis remains debated. Only takes precise nuclear cross-section measurements. Only takes spectroscopic observations of ancient stars. Only takes comparing theoretical yields with observed abundances. Matter-antimatter asymmetry presents another early universe puzzle. Particle physics suggests matter and antimatter should have been produced in equal quantities, yet the observable universe is overwhelmingly matter-dominated. Baryogenesis mechanisms require conditions identified by Sakharov baryon number violation C and CP violation and departure from thermal equilibrium. While CP violation exists in the Standard Model, it appears insufficient to account for the observed asymmetry. Proposed extensions include leptogenesis scenarios, in which heavy neutrino decays generate lepton asymmetry, converted to baryon asymmetry, through electroweak processes. Only takes slight imbalance in early interactions. Only takes violation of symmetry conditions. Only takes survival of 1 part in a billion excess baryons after annihilation. The electroweak epoch around 10 to the power of -12 seconds marks when electromagnetic and weak forces differentiated as the Higgs field acquired a vacuum expectation value. Earlier, still at higher energies, strong and electroweak interactions may have unified under grand unified theories, though no experimental confirmation exists. Phase transitions during these epochs could have generated topological defects, such as cosmic strings, though observational constraints limit their abundance. Only takes symmetry breaking to differentiate forces. Only takes cooling below critical temperatures. Only takes vacuum expectation values to reshape interaction strengths. Dark matter's origin may also lie in early universe physics. Thermal freeze-out models propose that dark matter particles were once in equilibrium with radiation. As expansion reduced temperature below particle mass, annihilation rates fell below expansion rates, leaving relic abundance fixed. The resulting density depends on annihilation cross-section linking cosmology with particle properties. Alternatively, non-thermal production mechanisms such as freeze-in or axion misalignment offer different pathways. Only takes comparing interaction rate with Hubble expansion rate. Only takes decoupling to preserve relic populations. Only takes measuring present density to constrain early cross-sections. Inflation itself raises deeper questions. What field drove it? What potential shape governed slow-roll behavior? Did inflation occur once or in multiple stages? Some models predict eternal inflation, where quantum fluctuations cause different regions to inflate at different rates, potentially generating a multiverse with varying physical constants. Such ideas extend beyond direct observational test, yet arise naturally from certain potentials. Only takes stochastic fluctuations of scalar fields. Only takes exponential expansion to create causal isolation. Only takes anthropic reasoning to interpret parameter distributions. The reheating phase following inflation transferred energy from the inflaton field into standard particles, repopulating the universe with radiation. The precise mechanism remains model-dependent, involving parametric resonance or perturbative decay. Observational constraints on reheating temperature influence predictions for relic particle abundances and gravitational wave backgrounds. Future detectors sensitive to stochastic gravitational wave spectra may probe these early epochs indirectly. Only takes converting vacuum energy into particle excitations. Only takes coupling constants to determine decay efficiency. Only takes background ripples to preserve memory. The early universe thus serves as both laboratory and boundary. Laboratory because extreme temperatures and densities test particle physics under conditions unreachable on Earth. Boundary because extrapolation approaches energies where known theories falter. Each relic measurement, microwave background, anisotropy, light element, abundance, large-scale structure, distribution, constrains models of the first seconds. Yet before inflation, before Planck time, before quantum gravity unification, understanding fades. Only takes pushing equations backward to reveal ignorance. Only takes combining observation with theory to narrow plausible histories. Only takes accepting that initial conditions may reflect deeper principles not yet formulated. The narrative of cosmic origins is neither static nor complete. It evolves as detectors refine, as particle accelerators probe higher energies, as theoretical frameworks mature. From plasma fluctuations to galaxy clusters, from symmetry to structure. The arc of early universe cosmology links quantum processes with macroscopic architecture. The expansion that continues today began in conditions far removed from present intuition. In tracing that trajectory, cosmology moves not toward final answers, but toward increasingly constrained questions. The beginning remains a frontier compressed in time, yet expansive in implication, where gravity, quantum fields, and thermodynamics intersect in the briefest instants that shaped everything that followed. The search for life beyond Earth extends cosmology's scale down to biology linking planetary chemistry with stellar evolution and galactic context. Astrobiology does not assume rarity or abundance. It measures conditions and probabilities. The observable universe contains hundreds of billions of galaxies, each with billions of stars, and surveys over the past 3 decades have confirmed that planetary systems are common rather than exceptional. The first confirmed detection of an exoplanet orbiting a Sun-like star was announced in 1995 by Michel Mayor and Didier Queloz, who identified 51 Pegasi b through radial velocity measurements, revealing periodic Doppler shifts in its host star. Only takes precision spectroscopy, capable of detecting stellar motion of a few meters per second. Only takes interpreting periodic shifts as gravitational tug. Only takes confirmation across multiple cycles to establish orbit. Since then, thousands of exoplanets have been catalogued through transit photometry, radial velocity, microlensing, and direct imaging. The Kepler mission demonstrated that small Earth-sized planets are common, many residing in their star's habitable zone, where temperatures allow liquid water under suitable atmospheric conditions. The habitable zone is not a guarantee of life, but a thermodynamic criterion. Only takes orbital distance and stellar luminosity to define boundaries. Only takes greenhouse gases to widen or narrow that band. Only takes atmospheric composition to determine surface conditions. Planetary habitability depends on multiple factors beyond orbital radius, planetary mass, sufficient to retain atmosphere magnetic field, to shield from stellar wind, geologic activity, to regulate carbon cycles and stable stellar output over billions of years. M-dwarf stars abundant in the galaxy possess narrow habitable zones close to the star, raising concerns about tidal locking and flare activity. Yet their longevity offers extended timeframes for biological evolution. Only takes balancing radiation hazards against time availability. Only takes modeling atmospheric escape rates. Only takes climate simulations incorporating rotation and cloud feedback. Spectroscopic analysis of exoplanet atmospheres now probes chemical composition during transits as starlight filters through planetary atmospheres, imprinting absorption lines. Detection of molecules such as water vapor, methane, carbon dioxide, and oxygen informs assessments of potential biosignatures. However, interpreting biosignatures requires caution. Abiotic processes can mimic biological signatures under certain conditions. Only takes photochemistry to produce oxygen without life. Only takes volcanic outgassing to generate methane. Only takes contextual planetary modeling to distinguish sources. The Drake equation offers a probabilistic framework for estimating the number of communicative civilizations in the galaxy, incorporating factors such as star formation, rate fraction of stars with planets, number of habitable planets per system fraction, developing life fraction, evolving intelligence, and communicative longevity. While some parameters are now empirically constrained, others remain speculative. Only takes multiplying probabilities to reveal uncertainty. Only takes narrowing astrophysical factors to shift emphasis toward biological unknowns. Only takes recognizing that longevity dominates outcome. The Fermi paradox sharpens the inquiry. If technological civilizations are common, why is there no clear evidence of their presence? Proposed resolutions range from rarity of life to self-limiting technological lifespans, to communication modes undetectable by current methods, to simple vastness of space and time diluting signals. The search for extraterrestrial intelligence CD monitors radio frequencies and optical pulses for artificial patterns. To date, no confirmed extraterrestrial signal has been detected. Only takes scanning billions of frequency channels. Only takes distinguishing narrowband artificial signals from natural astrophysical noise. Only takes patience across decades of monitoring. Within our solar system, attention focuses on environments that may host microbial life. Mars exhibits geological features indicative of past liquid water, including valley networks and sedimentary deposits. Missions, such as those by NASA rovers, analyze mineralogy and search for organic molecules preserved in ancient rocks. Europa and Enceladus, icy moons of Jupiter and Saturn, respectively harbor subsurface oceans beneath ice crusts evidenced by induced magnetic fields and plume activity. Hydrothermal vents on Earth support ecosystems independent of sunlight, suggesting analogous potential in subsurface oceans elsewhere. Only takes tidal heating to maintain liquid water beneath ice. Only takes chemical gradients to power metabolism. Only takes drilling or plume sampling to access subsurface environments. The origin of life on Earth remains uncertain, complicating extrapolation. Hypotheses include primordial soup chemistry, energized by lightning hydrothermal vent catalysis along mineral surfaces, and RNA world scenarios where self-replicating molecules preceded cellular life. The early Earth experienced heavy bombardment, yet isotopic evidence suggests life emerged relatively quickly once conditions stabilized. Only takes complex organic molecules forming spontaneously under certain conditions. Only takes encapsulation within lipid membranes. Only takes replication with variation to initiate evolution. Exoplanet characterization advances with next-generation telescopes capable of direct imaging coronagraphy and starshade concepts to suppress stellar glare. High-contrast imaging may eventually detect Earth-like planets around nearby stars, allowing spectroscopy of reflected light. Detecting disequilibrium chemistry, for instance, coexistence of oxygen and methane far from thermodynamic equilibrium, could provide stronger biosignature evidence. Yet definitive confirmation would require ruling out non-biological pathways with high confidence. Only takes refining spectral resolution. Only takes extended integration times to gather photons from faint worlds. Only takes interdisciplinary modeling spanning astrophysics, chemistry, and biology. Galactic context influences habitability as well. Regions with high supernova rates may subject planets to sterilizing radiation, while low metallicity regions may lack sufficient heavy elements to form rocky planets. The concept of a galactic habitable zone considers radial distance from galactic center, balancing metallicity and radiation environment. Only takes mapping metallicity gradients. Only takes modeling cosmic ray flux. Only takes considering billions of years of stellar evolution. Technosignatures extend beyond radio signals. Megastructures altering stellar light curves, waste heat detectable in infrared or atmospheric industrial pollutants could indicate advanced civilizations. Searches for anomalous transit signatures or excess mid-infrared emission examine such possibilities, though none have yielded confirmed evidence. Only takes systematic surveys of stellar brightness variations. Only takes filtering natural variability from artificial hypotheses. Only takes cautious interpretation to avoid overreach. The psychological dimension accompanies scientific inquiry. Discovering microbial life within our solar system would imply that life emerges readily under suitable conditions. Detecting atmospheric biosignatures on an exoplanet would suggest that biology is not unique to Earth. Confirming intelligent signals would transform philosophical and cultural frameworks. Yet absence of evidence, particularly across limited search windows, does not equate to evidence of absence. Only takes recognizing sampling limits. Only takes expanding observational coverage. Only takes maintaining methodological rigor. Astrobiology integrates planetary science, stellar astrophysics, atmospheric chemistry, geology, and evolutionary biology. It translates cosmic conditions into biological potential. While cosmology addresses origin and fate of the universe, astrobiology asks whether consciousness arises elsewhere within it. The observable universe expands under dark energy, structured by dark matter, seeded by inflationary fluctuations. Within one galaxy among billions, life emerged on a rocky planet, orbiting an ordinary star. Whether this event is commonplace or exceptional remains undetermined. Only takes continued exploration of nearby planets and distant atmospheres. Only takes refining detection methods for subtle biosignatures. Only takes confronting the silence of the sky with measured persistence. The search proceeds not as assumption, but as investigation grounded in spectroscopy, orbital mechanics, chemistry, and statistical inference. In probing other worlds, humanity studies itself indirectly, testing whether its existence reflects universal tendencies or rare contingencies. The answer may arrive gradually through spectra and samples rather than proclamation. Until then, the cosmos remains biologically unconfirmed beyond Earth, vast in possibility, quiet in response, awaiting further observation. Cosmology ultimately confronts limits, not only of distance and energy, but of knowledge itself. The observable universe is bounded by a particle horizon determined by the finite age of cosmic expansion and the finite speed of light. Beyond that horizon, regions may exist with properties inaccessible to measurement, separated not by material barrier, but by causal disconnection. Only takes finite cosmic age to define observable radius. Only takes integrating the scale factor over time to compute co-moving distance. Only takes recognizing that expansion outpaces photon travel in certain regimes. The cosmic event horizon differs subtly. It marks the boundary beyond which events occurring now will never be observed in the future, because accelerated expansion prevents their light from ever reaching us. In a universe dominated by dark energy consistent with a cosmological constant, this horizon stabilizes at a finite distance. Galaxies currently visible may eventually cross it, their emitted photons redshifting beyond detectability. Only takes persistent acceleration to impose permanent observational limits. Only takes exponential growth of the scale factor. Only takes considering asymptotic futures to define causal boundaries. The question of whether the universe extends infinitely beyond the observable patch remains open. Observations indicate spatial flatness within small uncertainty margins, consistent with either infinite Euclidean geometry or a finite but unobservably large topology. Certain compact topologies could in principle imprint repeating patterns in the cosmic microwave background, yet no definitive signatures have been found. Only takes mapping temperature correlations across large angles. Only takes searching for matched circles in the sky. Only takes acknowledging that absence of pattern constrains, but does not eliminate possibilities. The multiverse hypothesis extends beyond observational cosmology into speculative territory. In eternal inflation scenarios, quantum fluctuations of the inflaton field generate regions where inflation ends at different times, creating bubble universes with potentially varying physical constants. String theory landscapes propose vast numbers of metastable vacuum states, each corresponding to different parameter sets. Whether these constructs represent physical reality or mathematical extrapolation remains debated. Only takes extrapolating inflationary dynamics stochastically. Only takes accepting anthropic selection to interpret parameter tuning. Only takes distinguishing between falsifiable and unfalsifiable frameworks. The fine-tuning problem motivates such speculation. Fundamental constants. The strength of electromagnetic coupling, the cosmological constant magnitude particle mass ratios, appear within narrow ranges compatible with complex structure formation. Slight deviations in nuclear force strength could prevent stable carbon production in stars. Modest increases in dark energy density could suppress galaxy formation entirely. Whether this apparent tuning reflects deep physical necessity or selection among many possibilities remains unsettled. Only takes sensitivity analysis of stellar nucleosynthesis pathways. Only takes adjusting parameters in structure formation simulations. Only takes confronting coincidence with explanation. Another frontier concerns quantum gravity, the integration of general relativity with quantum mechanics. General relativity describes space-time curvature smoothly, while quantum field theory operates on fixed background geometries with probabilistic excitations, near singularities. Whether at black hole centers or at the universe's origin, both frameworks are simultaneously required, yet incompatible in current formulations. Approaches include string theory, loop, quantum gravity, causal dynamical triangulations, and asymptotic safety programs. None has achieved empirical confirmation. Only takes curvature scales approaching Planck length to necessitate new theory. Only takes incompatibility of renormalization in perturbative quantum gravity. Only takes theoretical consistency checks to advance proposals. Observational cosmology continues tightening constraints on parameters, yet some quantities remain limited by cosmic variance. Statistical uncertainty inherent because we observe only one realization of the universe. Large-angle fluctuations in the cosmic microwave background cannot be averaged across multiple universes. They are unique to our observable patch. Only takes finite sample size to impose irreducible uncertainty. Only takes acknowledging that some statistical limits are fundamental. Only takes separating measurement precision from cosmic variance boundaries. Time also imposes epistemic constraints. Billions of years hence, cosmic acceleration may render extragalactic astronomy impossible for observers in gravitationally bound systems like the local group. The cosmic microwave background will redshift beyond detectability. Evidence for Big Bang cosmology could fade. The present epoch may represent a uniquely informative window in which multiple independent lines of evidence converge. Only takes cosmological evolution to alter accessible data. Only takes imagining future observers without background radiation detection. Only takes recognizing contingency of observational opportunity. Entropy provides another axis of limitation. The second law of thermodynamics dictates increasing entropy in closed systems and cosmology extends this principle to universal scale. As stars exhaust nuclear fuel and black holes eventually evaporate via Hawking radiation over unimaginably long timescales, the universe trends toward thermodynamic equilibrium. In such a state, free energy gradients diminish, reducing capacity for structure and computation. Only takes irreversible processes to increase entropy. Only takes gravitational clustering to create local order at expense of global disorder. Only takes considering far future timescales to envision heat death. Yet even heat death assumes persistence of known physical laws. Hypothetical vacuum decay, wherein our universe resides in a metastable vacuum state that could transition to a lower energy configuration via quantum tunneling, introduces another speculative limit. Such a transition would propagate at near light speed, altering fundamental constants within the bubble of true vacuum. While no evidence suggests imminent instability, particle physics measurements of Higgs boson and top quark masses leave open questions regarding vacuum stability. Only takes evaluating effective potential of scalar fields. Only takes small parameter shifts to alter stability classification. Only takes acknowledging that cosmic longevity may depend on subtle quantum properties. Cosmology thus operates at intersection of empirical measurement and theoretical extrapolation. Its equations describe expansion history with precision, yet its ultimate boundary conditions remain partly inferred. The observable universe yields data through photons, neutrinos, gravitational waves, and cosmic rays. Each messenger extends reach but also reveals constraint. Only takes combining multi-messenger astronomy to enhance inference. Only takes refining detector sensitivity to push horizons outward incrementally. Only takes admitting that some domains may remain permanently beyond access. Despite these limits, cosmology achieves coherence across scales spanning over 60 orders of magnitude in length and energy. From Planck scale fluctuations, potentially seeding inflationary perturbations, to superclusters spanning hundreds of millions of light-years, a unified mathematical framework describes evolution. General relativity governs expansion and gravitational collapse. Quantum field theory governs particle interactions. Thermodynamics governs energy flow. Their incomplete integration does not negate their collective explanatory power within tested domains. Only takes acknowledging provisional status of models. Only takes continued dialogue between observation and theory. Only takes revising frameworks when discrepancies persist. The narrative of cosmology is cumulative rather than final. Each resolved anomaly uncovers deeper questions. The Hubble tension challenges expansion inference. Dark matter challenges particle identification. Dark energy challenges vacuum interpretation. Black holes challenge quantum consistency. Inflation challenges initial conditions. Astrobiology challenges uniqueness assumptions. Multiverse proposals challenge falsifiability criteria. Only takes confronting successive frontiers to sustain inquiry. Only takes resisting premature closure. Only takes balancing skepticism with openness. In the end, cosmology does not promise omniscience. It promises structured uncertainty constrained by evidence. The universe may extend beyond observable horizons indefinitely. It may be one domain among many. It may conceal physics beyond current formulation. Yet within our horizon, measurable phenomena continue yielding insight. The expansion rate can be refined, background radiation mapped, gravitational waves detected, exoplanet atmospheres analyzed. Knowledge grows asymptotically approaching, but perhaps never reaching totality. Only takes recognizing that boundaries define investigation. Only takes humility before scale. Only takes persistence to continue mapping a cosmos that is at once mathematically describable and existentially vast. Observation is the discipline that binds cosmology's abstractions to measurable reality. Without instruments, equations remain speculation. Without theory, data remain catalogs. The history of modern cosmology is therefore inseparable from the evolution of telescopes, detectors, and analysis methods that translate faint signals into structured inference. Optical astronomy, once limited to ground-based refractors and reflectors, now operates across the electromagnetic spectrum from radio wavelengths thousands of meters long to gamma rays measured in fractions of nanometers. Each band reveals different physical processes. Only takes matching wavelength to mechanism. Only takes recognizing that hot plasma radiates in X-rays while cold molecular clouds glow in radio. Only takes building detectors tuned to specific photon energies. Radio astronomy maps neutral hydrogen through its 21-centimeter hyperfine transition line, allowing reconstruction of galactic rotation curves and large-scale structure distribution. Interferometric arrays combine signals from widely separated antennas, synthesizing apertures spanning kilometers. The technique relies on Fourier transforms correlating phase differences to reconstruct sky brightness. Only takes preserving phase coherence across antennas. Only takes atomic clock synchronization. Only takes computational inversion to transform interference fringes into images. Optical and infrared telescopes capture starlight and galaxy spectra, enabling redshift measurement through absorption and emission lines. Spectroscopy quantifies elemental composition, temperature, and velocity dispersion. From these data arise rotation curves, metallicity gradients, and expansion rates. Space-based observatories circumvent atmospheric absorption and turbulence, extending sensitivity and resolution. Only takes eliminating atmospheric seeing to sharpen images. Only takes cooling detectors to reduce thermal noise. Only takes long integration times to collect photons from distant galaxies. X-ray and gamma-ray astronomy probe extreme environments accreting black holes, neutron stars, supernova remnants, and active galactic nuclei. High-energy photons require grazing incidence mirrors or scintillation detectors rather than traditional reflective optics. These instruments detect signatures of relativistic processes and hot intergalactic gas. Only takes focusing shallow-angle reflections. Only takes shielding from background cosmic rays. Only takes spectral fitting to extract plasma temperatures. Beyond electromagnetic radiation, neutrino observatories detect nearly massless particles that traverse matter almost unimpeded. Massive detectors buried underground or beneath ice observe faint flashes produced when rare neutrino interactions occur. Such detections confirm processes within the Sun and supernovae, and may one day probe cosmic accelerators or early universe relic neutrino backgrounds. Only takes enormous target volumes to compensate for weak interaction cross-sections. Only takes photomultiplier arrays capturing Cherenkov radiation. Only takes correlating event timing to infer directionality. Gravitational wave astronomy adds a fundamentally new messenger. Laser interferometers measure minuscule distortions in spacetime caused by accelerating masses such as merging black holes and neutron stars. These detections confirm predictions of general relativity in the strong field regime and provide independent distance measurements. Only takes stabilizing kilometer-scale arms against seismic noise. Only takes vacuum systems maintaining optical path purity. Only takes matching observed waveforms to relativistic simulations. Data analysis in cosmology has grown inseparable from computation. Sky surveys generate petabytes of data requiring automated pipelines for calibration, object detection, and classification. Statistical inference employs Bayesian frameworks to compare models with data marginalizing over nuisance parameters and quantifying uncertainties. Only takes defining likelihood functions accurately. Only takes sampling parameter space efficiently. Only takes guarding against selection biases. Large sky surveys map millions of galaxies constructing three-dimensional distributions through redshift catalogs. From these maps emerge baryon acoustic oscillation scales, correlation functions, and power spectra. Weak gravitational lensing surveys measure subtle distortions in galaxy shapes to map dark matter distribution statistically. Only takes correcting for instrumental point spread functions. Only takes calibrating photometric redshifts. Only takes averaging over vast samples to detect minute shear signals. Calibration remains central. Standard candles such as Type 1, a supernovae, require understanding of intrinsic luminosity variation and environmental effects. Standard rulers such as baryon acoustic oscillations depend on precise modeling of sound horizon scales from early universe physics. Only takes cross-checking independent calibration methods. Only takes iterative refinement as datasets grow. Only takes transparency in systematic uncertainty reporting. Cosmology's precision era has emerged within the past few decades. Parameter estimation now constrains Hubble constant matter density, baryon density, spectral index, and optical depth with remarkable precision. Yet precision does not guarantee completeness. Tensions between datasets highlight potential unknown systematics or new physics. Only takes independent measurements disagreeing slightly. Only takes shrinking error bars to amplify discrepancy. Only takes resisting premature reconciliation. The sociology of large collaborations shapes modern cosmology. Projects involve hundreds to thousands of researchers requiring coordination across institutions and continents. Data releases undergo internal review processes before publication. Authorship reflects collective effort rather than individual discovery. Only takes collaborative frameworks to manage complexity. Only takes shared software and standardized pipelines. Only takes balancing openness with quality control. Instrument design anticipates future questions. Surveys are planned not merely to confirm existing models, but to test their limits. Sensitivity improvements target specific parameters, equation of state deviations, neutrino mass sum non-Gaussianity in primordial fluctuations. Only takes defining science goals clearly. Only takes engineering tolerances matching theoretical needs. Only takes maintaining long-term funding and institutional commitment. Cosmology's interplay with particle physics continues through laboratory experiments complementing astronomical observation. Measurements of neutrino oscillation parameters inform cosmological modeling of structure growth. Collider experiments constrain properties of hypothetical dark matter candidates. Only takes integrating cross-disciplinary results. Only takes reconciling scales spanning laboratory to cosmic horizon. Only takes maintaining dialogue between communities. The epistemology of cosmology acknowledges both strength and limitation. Unlike laboratory sciences, controlled experiments on cosmic scale are impossible. Instead, cosmologists infer from natural experiments embedded in space-time. Observations capture single realizations of processes occurring once. Yet reproducibility arises through independent measurements and cross-validation across methods. Only takes verifying predictions through multiple channels. Only takes aligning theoretical expectations with diverse datasets. Only takes distinguishing between model-dependent inference and direct measurement. As instrumentation improves, sensitivity extends to fainter and more distant signals. Yet practical limits arise from foreground contamination, dust emission, atmospheric noise, instrumental drift. Removing foregrounds requires modeling astrophysical sources unrelated to primary cosmological signals. Only takes characterizing galactic dust polarization. Only takes subtracting zodiacal light contributions. Only takes quantifying instrumental systematics rigorously. Artificial intelligence and machine learning increasingly assist in pattern recognition, anomaly detection, and parameter estimation. Neural networks classify galaxies, detect transients, and accelerate simulations. Yet interpretability and bias control remain essential. Only takes training datasets representative of true distributions. Only takes validating algorithms against simulated benchmarks. Only takes maintaining human oversight in automated pipelines. Cosmology thus becomes a synthesis of physics, engineering, statistics, and computation. Each observational advance sharpens theoretical challenge. Each theoretical refinement motivates new measurement. The universe does not yield its structure readily. It requires instruments sensitive to photons that have traveled billions of years, to ripples in space-time smaller than atomic nuclei, to neutrinos passing silently through Earth. Only takes extending senses through technology. Only takes patience measured in decades-long missions. Only takes willingness to revise models when evidence demands. The trajectory forward will likely involve increasingly precise surveys mapping structure and expansion simultaneously, deeper searches for dark matter interactions, more sensitive gravitational wave detectors, probing early universe backgrounds, and improved exoplanet characterization instruments. Observation remains finite in reach, yet expansive in ambition. Within causal horizons, cosmology continues translating faint signals into coherent narrative. It does so not by assuming final answers, but by refining measurement, calibrating uncertainty, and confronting discrepancy openly. Only takes aligning theory with instrument capability. Only takes maintaining methodological rigor across collaborations. Only takes continuing the disciplined conversion of light waves and particles into understanding. Mathematics is the quiet architecture beneath cosmology, the language that allows curvature, expansion, fluctuation, and entropy to be stated precisely rather than poetically. The universe does not announce its geometry. It reveals it through equations relating matter-energy content to space-time curvature. General relativity encodes this relationship in tensor form, equating the Einstein tensor representing geometry with the stress-energy tensor representing content. The field equations are compact in notation, yet expansive in implication. Curvature tells matter how to move. Matter tells curvature how to bend. Only takes differentiable manifolds to model spacetime. Only takes metric tensors to measure interval. Only takes covariant derivatives to express curvature invariantly. The Friedmann-Lemaitre-Robertson-Walker metric simplifies this structure by assuming homogeneity and isotropy on large scales, reducing the complexity of spacetime to a single scale factor evolving in time. From this ansatz emerge the Friedmann equations relating expansion rate to energy density components, radiation matter, curvature, and cosmological constant. These equations predict decelerating or accelerating behavior depending on dominant component. Only takes symmetry assumptions to reduce degrees of freedom. Only takes inserting perfect fluid stress energy. Only takes solving ordinary differential equations to obtain cosmic history. Perturbation theory refines this homogeneous picture, introducing small fluctuations around the background metric. Linear perturbation analysis decomposes density variations into Fourier modes, tracking their evolution through radiation and matter domination. The growth factor quantifies amplification of perturbations under gravitational instability. Only takes expanding equations to first order. Only takes assuming small amplitude initial fluctuations. Only takes computing transfer functions to connect primordial spectrum with present structure. The primordial power spectrum itself is often parameterized as a nearly scale-invariant function, characterized by amplitude and spectral index. Inflationary models predict slight deviations from perfect scale invariance encoded in the tilt parameter ns. Observations constrain ns to values slightly below unity, consistent with slow-roll inflation scenarios. Only takes differentiating inflaton potential to determine spectral tilt. Only takes mapping multipole moments of microwave background anisotropies. Only takes statistical estimation to extract parameter values. Statistical mechanics also permeates cosmology. The cosmic microwave background exhibits near-perfect blackbody spectrum described by Planck distribution. Entropy density scales with temperature cubed, while photon number density follows thermodynamic relations derived from Bose-Einstein statistics. Only takes applying equilibrium statistical physics to early universe plasma. Only takes tracking entropy conservation during adiabatic expansion. Only takes quantifying decoupling when interaction rates fall below Hubble expansion rate. Topology and differential geometry influence possible global structures of the universe. Compact manifolds with different identifications may yield identical local curvature, yet distinct global properties. The classification of three-dimensional manifolds underlies considerations of cosmic topology. Only takes identifying fundamental domains. Only takes analyzing geodesic closure conditions. Only takes connecting topology with observable correlation patterns. Quantum field theory in curved spacetime extends flat space particle concepts into expanding backgrounds. Particle creation in time-dependent metrics demonstrates that vacuum state depends on observer and geometry. Hawking radiation and inflationary fluctuation generation both arise from such formalism. Only takes quantizing fields on non-static backgrounds. Only takes Bogoliubov transformations between mode functions. Only takes computing expectation values of stress-energy tensors. Numerical relativity solves Einstein's equations in regimes where analytic solutions are unattainable, such as merging black holes or neutron-star collisions. Discretizing spacetime on computational grids, evolving metric components under constraint equations, and maintaining stability under nonlinear dynamics require sophisticated algorithms. Only takes choosing appropriate gauge conditions. Only takes implementing constraint damping schemes. Only takes verifying convergence across resolution scales. Cosmological parameter inference relies on Bayesian statistics, expressing posterior probability as product of likelihood and prior. Markov chain Monte Carlo methods explore high-dimensional parameter spaces sampling distributions consistent with observational data. Only takes defining informative yet non-restrictive priors. Only takes ensuring chain convergence. Only takes interpreting credible intervals carefully. Information theory provides additional perspective. The entropy of cosmological horizons, the information content of cosmic microwave background maps, and limits imposed by finite data sets all intersect with Shannon entropy and mutual information concepts. Only takes quantifying bits required to encode sky maps. Only takes evaluating compressibility of Gaussian random fields. Only takes recognizing that cosmic variance limits information extraction. Differential equations governing nucleosynthesis, recombination, and structure formation are stiff and coupled, requiring numerical integration across vast dynamic ranges. Codes such as those solving Boltzmann equations for photon-baryon fluid evolution compute anisotropy spectra with precision. Only takes solving coupled integro-differential systems. Only takes approximations validated against exact solutions. Only takes benchmarking against independent implementations. Renormalization concepts bridge cosmology and particle physics. Running coupling constants evolve with energy scale affecting early universe interactions. Effective field theories describe inflationary perturbations without committing to specific high-energy completions. Only takes separating low-energy observables from high-energy unknowns. Only takes expanding action in allowed operators respecting symmetries. Only takes constraining coefficients through data. Symmetry principles guide model construction. Lorentz invariance underlies relativity. Gauge symmetries structure particle interactions. Diffeomorphism invariance enforces coordinate independence. Breaking or modifying these symmetries carries measurable consequences. Only takes testing Lorentz invariance through high-energy astrophysical observations. Only takes searching for anisotropies violating isotropy. Only takes evaluating conservation laws derived from Noether's theorem. Even philosophical considerations about infinity boundary conditions and initial states translate into mathematical formalism. Whether time extends infinitely backward, whether space is finite or infinite, whether singularities represent physical entities or coordinate artifacts. Each question demands rigorous definition within mathematical structures. Only takes distinguishing between coordinate singularity and curvature singularity. only takes defining geodesic completeness, only takes evaluating invariance to characterize physical divergence. Mathematics does not guarantee truth, it guarantees consistency. Physical validity arises when mathematical structures correspond with observation. Cosmology's success lies in the sustained alignment between predictive equations and measured phenomena across vast scales. Yet mathematics also reveals possibilities beyond observation, generating models not yet empirically accessible. Only takes exploring solution spaces of field equations. Only takes perturbing parameters to test stability. Only takes maintaining skepticism about elegance absent evidence. As cosmology advances, new mathematics may emerge from attempts to unify gravity and quantum mechanics. Non-commutative geometry, higher dimensional manifolds, holographic dualities, and categorical frameworks represent explorations at theoretical frontier. Whether these abstractions describe physical reality remains contingent on future observation. Only takes deriving testable predictions. Only takes connecting abstract constructs with measurable signatures. Only takes refining both sides iteratively. In the ongoing dialogue between universe and equation, mathematics serves not as decoration, but as infrastructure. It compresses complexity into symbolic clarity, enabling extrapolation beyond immediate sensory experience. From tensor calculus describing curvature to statistical estimators extracting faint signals from noise from differential equations, modeling plasma oscillations, to group theory structuring particle symmetries, the discipline underwrites cosmology's coherence. Only takes internal logical consistency. Only takes empirical confrontation. Only takes readiness to revise when discrepancy appears. The cosmos may exceed any single framework, yet mathematics remains the instrument through which its patterns are articulated. Within causal horizons and observational limits, equations continue mapping expansion, fluctuation, and fate not as final answers, but as progressively refined approximations to a reality vast, structured, and partially knowable through the disciplined union of abstraction and evidence. Mathematics is the quiet architecture beneath cosmology, the language that allows curvature, expansion, fluctuation, and entropy to be stated precisely rather than poetically. The universe does not announce its geometry. It reveals it through equations relating matter-energy content to space-time curvature. General relativity encodes this relationship in tensor form, equating the Einstein tensor representing geometry with the stress-energy tensor representing content. The field equations are compact in notation, yet expansive in implication. Curvature tells matter how to move. Matter tells curvature how to bend. Only takes differentiable manifolds to model spacetime. Only takes metric tensors to measure interval. Only takes covariant derivatives to express curvature invariantly. The Friedmann-Lemaitre-Robertson-Walker metric simplifies this structure by assuming homogeneity and isotropy on large scales, reducing the complexity of spacetime to a single scale factor evolving in time. From this ansatz emerge the Friedmann equations relating expansion rate to energy density components, radiation matter, curvature, and cosmological constant. These equations predict decelerating or accelerating behavior depending on dominant component. Only takes symmetry assumptions to reduce degrees of freedom. Only takes inserting perfect fluid stress energy Only takes solving ordinary differential equations to obtain cosmic history. Perturbation theory refines this homogeneous picture, introducing small fluctuations around the background metric. Linear perturbation analysis decomposes density variations into Fourier modes, tracking their evolution through radiation and matter domination. The growth factor quantifies amplification of perturbations under gravitational instability. Only takes expanding equations to first order. Only takes assuming small amplitude initial fluctuations. Only takes computing transfer functions to connect primordial spectrum with present structure. The primordial power spectrum itself is often parameterized as a nearly scale-invariant function, characterized by amplitude and spectral index. Inflationary models predict slight deviations from perfect scale invariance encoded in the tilt parameter, NA. Observations constrain NS to values slightly below unity, consistent with slow-roll inflation scenarios. Only takes differentiating inflaton potential to determine spectral tilt. Only takes mapping multipole moments of microwave background anisotropies. Only takes statistical estimation to extract parameter values. Statistical mechanics also permeates cosmology. The cosmic microwave background exhibits near-perfect blackbody spectrum described by Planck distribution. Entropy density scales with temperature cubed, while photon number density follows thermodynamic relations derived from Bose-Einstein statistics. Only takes applying equilibrium statistical physics to early universe plasma. Only takes tracking entropy conservation during adiabatic expansion. Only takes quantifying decoupling when interaction rates fall below Hubble expansion rate. Topology and differential geometry influence possible global structures of the universe. Compact manifolds with different identifications may yield identical local curvature, yet distinct global properties. The classification of three-dimensional manifolds underlies considerations of cosmic topology. Only takes identifying fundamental domains. Only takes analyzing geodesic closure conditions. Only takes connecting topology with observable correlation patterns. Quantum field theory in curved spacetime extends flat space particle concepts into expanding backgrounds. Particle creation in time-dependent metrics demonstrates that vacuum state depends on observer and geometry. Hawking radiation and inflationary fluctuation generation both arise from such formalism. Only takes quantizing fields on non-static backgrounds. Only takes Bogoliubov transformations between mode functions. Only takes computing expectation values of stress energy tensors. Numerical relativity solves Einstein's equations in regimes where analytic solutions are unattainable, such as merging black holes or neutron-star collisions. Discretizing spacetime on computational grids, evolving metric components under constraint equations, and maintaining stability under nonlinear dynamics require sophisticated algorithms. Only takes choosing appropriate gauge conditions. Only takes implementing constraint damping schemes. Only takes verifying convergence across resolution scales. Cosmological parameter inference relies on Bayesian statistics, expressing posterior probability as product of likelihood and prior. Markov chain, Monte Carlo methods explore high-dimensional parameter spaces, sampling distributions, consistent with observational data. Only takes defining informative yet non-restrictive priors. only takes ensuring chain convergence, only takes interpreting credible intervals carefully. Information theory provides additional perspective. The entropy of cosmological horizons, the information content of cosmic microwave background maps, and limits imposed by finite data sets all intersect with Shannon entropy and mutual information concepts. Only takes quantifying bits required to encode sky maps. Only takes evaluating compressibility of Gaussian random fields. Only takes recognizing that cosmic variance limits information extraction. Differential equations governing nucleosynthesis, recombination, and structure formation are stiff and coupled, requiring numerical integration across vast dynamic ranges. Codes such as those solving Boltzmann equations for photon-baryon fluid evolution compute anisotropy spectra with precision. Only takes solving coupled integro-differential systems. Only takes approximations validated against exact solutions. Only takes benchmarking against independent implementations. Renormalization concepts bridge cosmology and particle physics. Running coupling constants evolve with energy scale affecting early universe interactions. Effective field theories describe inflationary perturbations without committing to specific high-energy completions. Only takes separating low-energy observables from high-energy unknowns. Only takes expanding action in allowed operators respecting symmetries. Only takes constraining coefficients through data. Symmetry principles guide model construction. Lorentz invariance underlies relativity. Gauge symmetries structure particle interactions. Diffeomorphism invariance enforces coordinate independence. Breaking or modifying these symmetries carries measurable consequences. Only takes testing Lorentz invariance through high-energy astrophysical observations. Only takes searching for anisotropies violating isotropy. Only takes evaluating conservation laws derived from Noether's theorem. Even philosophical considerations about infinity boundary conditions and initial states translate into mathematical formalism. Whether time extends infinitely backward, whether space is finite or infinite, whether singularities represent physical entities or coordinate artifacts, each question demands rigorous definition within mathematical structures. Only takes distinguishing between coordinate singularity and curvature singularity. Only takes defining geodesic completeness. Only takes evaluating invariance to characterize physical divergence. Mathematics does not guarantee truth. It guarantees consistency. Physical validity arises when mathematical structures correspond with observation. Cosmology's success lies in the sustained alignment between predictive equations and measured phenomena across vast scales. Yet mathematics also reveals possibilities beyond observation, generating models not yet empirically accessible. Only takes exploring solution spaces of field equations. Only takes perturbing parameters to test stability. Only takes maintaining skepticism about elegance absent evidence. As cosmology advances, new mathematics may emerge from attempts to unify gravity and quantum mechanics. Non-commutative geometry, higher dimensional manifolds, holographic dualities, and categorical frameworks represent explorations at theoretical frontier. Whether these abstractions describe physical reality remains contingent on future observation. Only takes deriving testable predictions. Only takes connecting abstract constructs with measurable signatures. only takes refining both sides iteratively. In the ongoing dialogue between universe and equation, mathematics serves not as decoration, but as infrastructure. It compresses complexity into symbolic clarity, enabling extrapolation beyond immediate sensory experience, from tensor calculus describing curvature to statistical estimators extracting faint signals from noise from differential equations, modeling plasma oscillations, to group theory structuring particle symmetries. The discipline underwrites cosmology's coherence. Only takes internal logical consistency. Only takes empirical confrontation. Only takes readiness to revise when discrepancy appears. The cosmos may exceed any single framework, yet mathematics remains the instrument through which its patterns are articulated. Within causal horizons and observational limits, equations continue mapping expansion, fluctuation, and fate not as final answers, but as progressively refined approximations to a reality vast, structured, and partially knowable through the disciplined union of abstraction and evidence. Structure formation translates primordial simplicity into cosmic complexity. Minute density fluctuations imprinted in the early universe, likely originating from quantum fluctuations, stretched during inflation, provided the seeds for all later galaxies, clusters, and filaments. These fluctuations are observed as temperature anisotropies in the cosmic microwave background, at the level of 1 part in 100,000. Only takes amplifying overdense regions through gravitational instability. Only takes allowing slightly denser regions to decelerate expansion relative to background. Only takes letting gravity transform linear perturbations into nonlinear collapse. In the linear regime, perturbation growth can be described analytically. Overdensities grow proportionally to the scale factor during matter domination. Radiation pressure suppresses growth before matter-radiation equality, imprinting characteristic scales in the power spectrum. Dark matter interacting gravitationally, but not electromagnetically, begins clustering earlier than baryonic matter, forming potential wells into which gas later falls. Only takes distinguishing collisionless from collisional components. Only takes computing transfer functions across cosmic epochs. Only takes connecting early universe plasma physics with later gravitational dynamics. Numerical simulations have become indispensable in tracing this process from initial Gaussian random fields to the intricate cosmic web observed today. Large-scale simulations track billions of particles representing dark matter to map filamentary networks spanning hundreds of millions of light-years. These filaments intersect at nodes corresponding to galaxy clusters, while vast voids occupy underdense regions. Only takes discretizing phase space to approximate continuous matter distribution. Only takes solving Poisson equation for gravitational potential repeatedly across time steps. Only takes comparing statistical outputs with galaxy surveys. Observationally, galaxy redshift surveys reveal this web-like distribution, confirming predictions of gravitational growth from nearly scale-invariant initial spectra. The baryon acoustic oscillation scale imprinted by sound waves in the early plasma provides a standard ruler in this distribution. That scale manifests as a subtle excess in galaxy pair separations, around 150 megaparsecs. Only takes propagating pressure waves before recombination. Only takes freezing acoustic imprint when photons decouple. Only takes measuring correlation functions across vast samples. Galaxy formation within dark matter halos involves complex baryonic physics. Gas cools radiatively, condenses toward halo centers, and fragments into stars. Feedback processes from supernova explosions and active galactic nuclei regulate star formation by heating or expelling gas. Without feedback, simulations overproduce stars compared to observations. Only takes including energy injection from stellar winds. Only takes modeling black hole accretion and jet outflows. Only takes iteratively refining subgrid prescriptions to match empirical scaling relations. Star formation histories vary with environment and mass. Massive galaxies tend to form stars earlier and quench sooner, a phenomenon sometimes termed downsizing, despite hierarchical assembly of dark matter halos. Environmental effects, such as ram pressure stripping in clusters, can remove gas from galaxies, suppressing further star formation. Only takes acknowledging that gravitational assembly and baryonic evolution need not align perfectly in timing. Only takes analyzing spectral energy distributions to infer stellar ages. Only takes incorporating hydrodynamic interactions in dense regions. Supermassive black holes reside in centers of most massive galaxies, with masses correlated to bulge properties, suggesting coevolution. Accretion episodes power luminous quasars visible across cosmic distances. These quasars provide probes of intergalactic medium through absorption lines in their spectra. Only takes interpreting red-shifted emission lines to estimate distances. Only takes mapping intervening gas clouds via absorption features. Only takes relating central black hole mass to stellar velocity dispersion. Clusters of galaxies represent largest gravitationally bound structures. They contain hundreds to thousands of galaxies embedded in hot intracluster plasma emitting X-rays. Gravitational lensing measurements reveal that most cluster mass resides in dark matter. Only takes measuring distortion of background galaxy shapes. Only takes applying hydrostatic equilibrium models to X-ray gas. Only takes reconciling baryonic fraction with cosmological parameters. Voids, conversely, are underdense regions expanding faster than average. Their dynamics provide complementary tests of cosmological models, because modified gravity theories may predict distinct behavior in low-density environments. Only takes surveying galaxy distribution to map void boundaries. Only takes modeling peculiar velocities within underdense regions. Only takes comparing growth rates with theoretical expectations. The intergalactic medium, though tenuous, contains significant fraction of baryons. After ionization, ultraviolet radiation from early stars and quasars ionized hydrogen, altering thermal history of gas. The Lyman alpha forest observed in quasar spectra traces fluctuations in this medium. Only takes simulating radiative transfer during ionization. Only takes correlating absorption line statistics with density fluctuations. Only takes constraining timing of ionization from polarization measurements of cosmic microwave background. Chemical evolution accompanies structure formation. The first generation of stars formed from pristine hydrogen and helium, synthesizing heavier elements through nuclear fusion and dispersing them via supernova explosions. Subsequent generations incorporated these metals enabling formation of planets and complex chemistry. Only takes tracking stellar nucleosynthesis yields. Only takes modeling metal enrichment of interstellar medium. Only takes observing elemental abundances in ancient stars to reconstruct early history. Magnetic fields pervade galaxies and clusters, though their origin remains uncertain. Dynamo processes may amplify weak seed fields generated in early universe or during structure formation shocks. Only takes coupling magnetohydrodynamics with gravitational collapse. Only takes measuring Faraday rotation to infer field strengths. Only takes integrating plasma physics with cosmological evolution. Cosmic rays, high-energy charged particles propagate through magnetic fields, influencing interstellar chemistry and gas dynamics. Feedback between cosmic rays and galactic winds may contribute to regulating star formation. Only takes incorporating relativistic particle populations into hydrodynamic models. Only takes observing gamma-ray emission from interactions. Only takes balancing multi-scale processes across orders of magnitude. Precision cosmology now leverages large datasets to constrain parameters governing structure growth. Weak gravitational lensing surveys measure subtle distortions of galaxy images to map mass distribution statistically. Redshift space distortions reveal peculiar velocities linked to growth rate of structure. Only takes disentangling geometric distortions from dynamical effects. Only takes controlling systematic uncertainties in shape measurement. Only takes comparing results with predictions of general relativity under assumed dark energy model. Tensions sometimes emerge between different measurements, such as discrepancies in amplitude of matter, fluctuations inferred from cosmic microwave background versus late-time surveys. Whether such tensions indicate new physics, unrecognized systematics, or statistical fluctuation remains under investigation. Only takes maintaining methodological rigor. Only takes cross-validating independent probes. Only takes resisting premature theoretical extrapolation. On smaller scales, dwarf galaxies pose challenges. Observed density profiles sometimes appear shallower than predicted by simple cold, dark matter simulations, raising questions about baryonic feedback effects or alternative dark matter properties. Only takes simulating high-resolution halos with detailed feedback. Only takes comparing stellar kinematics to inferred mass distributions. Only takes exploring models such as self-interacting dark matter cautiously. Large-scale homogeneity emerges statistically despite local complexity. Beyond scales of several hundred megaparsecs, matter distribution approaches uniformity, consistent with cosmological principle. Testing this assumption requires deep surveys mapping three-dimensional galaxy positions. Only takes calculating fractal dimension at increasing scales. Only takes ensuring survey completeness and selection corrections. Only takes verifying isotropy across different sky regions. Structure formation thus interweaves gravity, thermodynamics, plasma physics, nuclear processes, and relativistic dynamics. From nearly featureless early plasma, the universe evolves into hierarchical networks of matter with intricate internal processes. The same fundamental constants govern atomic transitions in distant galaxies and laboratories on Earth, linking microphysics with megaparsec scale patterns. Only takes following perturbations from quantum origin to nonlinear collapse. Only takes embedding local astrophysics within global expansion. Only takes sustaining dialogue between simulation and observation. In this narrative, humanity occupies a late epoch in which heavy elements forged in prior stellar generations assemble into planetary systems capable of reflection. The cosmic web extends far beyond observational reach, yet its statistical properties conform to predictions derived from simple initial conditions, plus gravitational amplification. Complexity arises not from arbitrary design, but from lawful evolution across immense spans of time and space. Only takes initial fluctuations. Only takes gravitational attraction. Only takes expansion setting boundary conditions. From these ingredients emerges galaxies, stars, planets, and observers capable of tracing the chain backward. Structure formation is therefore not a peripheral chapter, but central bridge between early universe physics and present cosmic landscape, demonstrating how minimal assumptions rigorously applied yield the rich architecture mapped by modern cosmology. Observation anchors cosmology to empirical discipline, transforming speculative geometry into measurable science. The universe cannot be manipulated experimentally, yet it can be interrogated through radiation and particles that have traversed cosmic distances. Every photon collected by a telescope carries encoded information about its origin path and the intervening medium. Only takes decoding wavelength shifts to infer expansion. Only takes measuring flux to estimate intrinsic luminosity and distance. Only takes comparing spectra to laboratory standards. The electromagnetic spectrum serves as cosmology's primary channel of information. Radio telescopes map neutral hydrogen via the 21-centimeter line, revealing large-scale structure and galactic rotation. Infrared observatories penetrate dust to uncover star-forming regions and distant red-shifted galaxies. Optical surveys catalog billions of galaxies while ultraviolet observations trace hot young stars. X-ray and gamma-ray instruments detect high-energy phenomena such as accreting black holes and galaxy cluster plasma. Only takes calibrating detectors across frequencies. Only takes correcting for atmospheric absorption in ground-based instruments. Only takes combining multi-wavelength data into coherent models. Distance measurement constitutes a central challenge because cosmological inference depends on mapping redshift to physical scale. The cosmic distance ladder employs successive rungs, parallax for nearby stars, standard candles such as Cepheid variables for intermediate distances, and Type 1a supernovae for cosmological scales. Each rung requires calibration by the preceding one. Only takes geometric baseline from Earth's orbit for parallax. Only takes period luminosity relation to standardize Cepheids. Only takes light curve shape corrections to standardize supernovae. Statistical uncertainties and systematic biases must be quantified meticulously because small calibration shifts propagate into cosmological parameter estimates. Survey design therefore emphasizes redundancy cross-checks and independent methods. Surface brightness fluctuations, gravitational lens time delays, and tip-of-the-red giant branch measurements provide alternative routes. Only takes diversifying methods to guard against hidden bias. Only takes transparent error propagation. Only takes open data allowing independent verification. Spectroscopy enriches imaging by providing detailed chemical and kinematic information. Emission and absorption lines reveal elemental abundances, ionization states, and velocities. Redshift surveys depend on precise spectral line identification to map three-dimensional structure. Only takes distinguishing cosmological redshift from peculiar velocity contributions. Only takes correcting for instrumental broadening. Only takes modeling stellar population synthesis to interpret integrated galaxy spectra. Gravitational lensing offers a powerful probe because it depends directly on mass rather than luminosity. Strong lensing produces multiple images and arcs, enabling measurement of mass distribution in galaxies and clusters. Weak lensing produces subtle distortions detectable statistically across millions of galaxies. Only takes measuring tiny ellipticity correlations. Only takes accounting for atmospheric and instrumental point spread functions. Only takes translating shear maps into matter power spectra. The cosmic microwave background remains a cornerstone dataset. Its temperature anisotropy spectrum encodes acoustic oscillations from the early universe constraining curvature matter density and baryon fraction. Polarization patterns add further constraints on ionization and inflationary parameters. Only takes decomposing sky maps into spherical harmonics. Only takes modeling foreground emission from our galaxy. Only takes comparing observed power spectra with theoretical predictions across multipoles. Large-scale surveys now integrate photometry and spectroscopy across vast sky fractions, generating petabyte-scale datasets. Data analysis requires sophisticated pipelines, machine learning classification, and high-performance computing. Only takes automating source detection. Only takes training algorithms on labeled samples. Only takes maintaining statistical rigor despite data volume. Cosmology increasingly overlaps with data science, yet interpretation must remain grounded in physical theory. Time-domain astronomy adds dynamic dimension by tracking transient events, supernovae, tidal disruption events, gamma-ray bursts. Monitoring sky variability improves understanding of stellar evolution and black hole accretion while refining cosmological probes. Only takes repeated imaging over months and years. Only takes distinguishing transient signals from noise. Only takes archiving light curves for cross-correlation. Neutrino and gravitational wave astronomy extend observational reach beyond photons. Neutrinos escape dense environments nearly unimpeded, providing information about core collapse supernovae and early universe processes. Gravitational waves reveal mergers of compact objects and test general relativity in strong field regimes. Only takes detecting minute space-time strain. Only takes triangulating signal arrival times across detectors. Only takes combining electromagnetic and gravitational observations for multi-messenger insight. Instrumentation itself reflects decades of engineering refinement. Adaptive optics compensates for atmospheric turbulence, sharpening ground-based images. Space telescopes avoid atmospheric distortion entirely, but face constraints of launch mass and maintenance. Interferometry combines signals from separated telescopes to achieve higher resolution. Only takes phase-stable signal combination. Only takes precise alignment and timing synchronization. Only takes continuous calibration against reference sources. Cosmological inference proceeds by constructing models with parameters describing expansion history, matter content, and initial perturbations, then fitting these models to data via statistical frameworks such as Bayesian analysis. Posterior distributions quantify uncertainties and correlations among parameters. Only takes defining likelihood functions carefully. Only takes exploring parameter space efficiently with sampling algorithms. Only takes distinguishing statistical significance from mere fluctuation. Selection effects and observational biases demand constant vigilance. Malmquist bias, for example, favors detection of intrinsically brighter objects at larger distances. Incomplete sky coverage or dust extinction can skew inferred distributions. Only takes modeling survey sensitivity thresholds. Only takes simulating mock catalogs to test pipeline performance. Only takes applying corrections consistently. The cosmological principle itself assumption of large-scale homogeneity and isotropy must be tested rather than presumed. Anisotropy searches examine cosmic microwave background for directional anomalies. Galaxy surveys test isotropy in clustering statistics. Only takes rotating coordinate systems to search for preferred directions. Only takes quantifying statistical significance of anomalies. Only takes resisting overinterpretation of low probability patterns. Collaboration defines modern cosmology. Large consortia coordinate instrument construction, data collection, analysis, and publication. Peer review and replication remain essential safeguards. Only takes transparent methodology. Only takes sharing code and calibration procedures. Only takes acknowledging uncertainties openly. Public communication also shapes the discipline, because cosmological discoveries capture imagination and influence educational priorities. Clear explanation without distortion sustains trust. Only takes separating confirmed results from speculative extensions. Only takes avoiding exaggeration of unresolved tensions. Only takes emphasizing provisional nature of scientific knowledge. Future observational programs aim to refine measurements of dark energy equation, of state map neutral hydrogen across cosmic dawn, and detect primordial gravitational waves. Each objective requires improved sensitivity and systematic control. Only takes incremental technological innovation. Only takes theoretical guidance to interpret new signals. Only takes patience because cosmological timescales dwarf human lifetimes while experiments unfold within them. Observation thus forms the empirical backbone of cosmology. Without measurement, equations remain abstractions. Without theory, data remain disconnected points. The dialogue between sky and mathematics gradually narrows uncertainty ranges, ruling out models inconsistent with accumulated evidence. Only takes persistent refinement. Only takes skepticism balanced with openness. Only takes adherence to methodological discipline. Through observation, cosmology converts distant light into quantitative history, tracing expansion structure, growth, and elemental synthesis. The universe cannot be rerun, but it can be read. Each dataset adds resolution to that reading, clarifying parameters and exposing new questions. In this iterative process, knowledge advances not by sudden finality, but by convergence of independent lines of evidence. Only takes careful measurement. Only takes critical comparison. only takes willingness to revise models when warranted. Empirical scrutiny remains the defining strength of cosmology, ensuring that even when confronting phenomena at the edge of comprehension, conclusions rest on systematically gathered and rigorously analyzed evidence rather than conjecture alone.